Good day, everyone. My name is Olivani Odueyemofio from Group 1, and I'm going to talk about instruction cycle. Here we talk about program instruction, then move on to how a program instruction is executed in a computer system. Then move on to the basic terminologies, then we talk about instruction cycle, then phases of the instruction cycle. So what is a program instruction? A set of program statements that perform a specific task, or a computer program consists of a set of program instructions. Each of the program statements perform a specific task. So we all know a program instructions, they are sets of instructions which perform a specific task. So let's move on to how a program instruction is executed in a computer system. So program instruction is executed through a series of steps called instruction cycle. The CPU starts program execution by fetching them one by one from the control unit. Then the CPU starts program execution by fetching them one by one. Then the control unit decodes the machine instructions. Let's move on to various terminologies. So we have the memory address registers, which is also known as the MAR. It specifies the address in memory for a read or write operation. Then we move on to memory buffer register, the MBR. It contains the value to be stored in the memory or the last value read from the memory. Then we move on to program counter, PC. The PC holds the address of the next instruction to be fetched. Then move on to instruction register, IR. The IR holds the last instruction fetched. So we move on to what is an instruction cycle. Instruction cycle is basically the cycle that the CPU follows from the start of a program until the end of a program in order to process instructions. So a program residing in the memory unit of the computer consists of a sequence of instructions, and this sequence are based on, or this sequence consists of four phases. So the phases of instruction cycle. One, the fetch phase, the fetching of program instructions from the memory. So here in this phase, the CPU sends PC to MAR and then sends the recommend to the control bus. To the After sending a recommend on the data bus, the memory returns the instruction, which is then stored at the particular address in the memory. Then the CPU copies the data from the data. The CPU copies the data from the data bus to the to the MBR and copies data from MBR to registers. After all this, the point is implemented to the next memory location so that the next instruction can be fetched from the memory. So we move on to the next one, which is decoding of instructions. In this phase, the CPU determines which operation or which instruction is fetched from the instruction and which action needs to be performed on the instruction. Third one, we move on to the read phase, reading of an effective address. This phase deals with the decision of the operation. So here the operation can be either memory type or non-memory type. Then move to execute phase, which is the last phase, execution of instruction. In this phase, the instruction is finally executed and the result of the instruction is stored on the and the result of the instruction is stored in the register. So here, after the execution of an instruction, the CPU prepares itself for the execution of the next instruction to be processed. Thank you.
Hello, good evening. I'm Emmanuel Adenyo presenting on information instruction format from Group 1. Before that, let's know what is instruction format. It's a specific layout or structured data structure that defines how machine instructions are encoded in the computer's memory and proceeded by its central processing unit. It's a crucial aspect of computer architecture, determine how operations are executed by the hardware. Now let's talk about the components of instruction format: source and destination registers. These fields indicate the registers that will be involved in the operation. The source register contains data used in the operation, while the destination register stores the data, the results. Let's talk about the immediate operands. Immediate operands talks about some instructions include an immediate value that's used as an operand for the operation. The value or the operand is often included directly in the instructions. Let's move to the next point, that is addressing mode. This field specifies how the operands or addresses of data are determined. Example, the indirect addressing, the direct addressing, and then immediate addressing. Let's talk about the next point, that is control bit. This bit controls various aspects of the instruction execution. For example, that's the conditional branching, and then the interrupt, and then flags. Now let's talk about this. The types of instruction formats: 0 addressed instruction, 1 addressed instruction, 2 addressed instruction, and then 3 addressed instruction. Now let's talk about it one. And then 0 addressed instruction has no operands, doesn't have any operand. The operands are implicit, meaning that they are defined by the instructions itself. For example, a 0 address add the contents of 2 registers together. Let's move to the 1 address instruction. They have only one operand. The operand is stored in a register that the instruction specifies the addresses of the register. For example, an instruction to add the contents of a register to a memory location would have only one operand for the location memory. Let's talk about the 2 address instruction, which has only 2 operands. The operands are stored in 2 registers, and then the instruction specifies the addresses of the registers. For example, let's talk about an example. An instruction to subtract the contents of 1 register from the contents of another register would have 2 operations for 2 registers. Let's move to the 3 address instructions, which has only 3 operands. The operands are stored in 3 registers, and then the instruction specifies the address of the register. For example, an instruction to multiply the the contents of 2 registers and then store the results in the 3rd register would have 3 operands for 2 registers and then the 3rd register. Now let's talk about the advantages of instruction format. It plays a role of determining the size of the instruction sets, which affects the code size, execution time, and then flexibility of the processor. Now let's know what instruction sets are. Instruction sets refers to the collection of machine level instructions that computer processors can execute. You get it? Now let's move to the next point. It's a crucial aspect of the computer architecture that specifies the structure and encoding of instructions that can be executed by a processor. It's also clear. It also provides a clear and then structured representation of operations, which enables efficiency, memory use, easy decoding, versatility, standardization, and then flexibility. Now let's move on to the disadvantages, which is also the challenges in instruction format, and that will be my last point. Instruction length. The instruction length talks about how the instruction format must be long enough to encode all of the necessary information, but it shouldn't be too long, as this will increase the time it takes to fetch and then decode instructions. And for example, let's say a 32-bit instruction can encode more than a 16 instruction, but it also take longer to fetch and then decode. Let's move to the number of operands. The instruction format must specify the number of operands for each instruction. The number of operands affects the flexibility of the instruction set, which we talked about earlier in the other slides. That instruction set refers to the collection of machine level instructions that computer processor can execute. For example, an instruction with 2 operands can perform more operations than an instruction with only 1 operand. Now let's move to the next point. That is the instruction encoding. The instruction format must be encoded in a way that is efficient and then easy to decode. For example, a variable length instruction format can be more efficient than a fixed length instruction format, but it's more difficult to decode. And then the encoding scheme should also be flexible enough to allow for future expansion of the instruction set. Now, this is the last point: instruction set compatibility. The instruction format must be compatible with existing softwares, which means that new instruction sets or new instructions should not break existing programs. For example, if a new instruction set is very important to make sure that the instruction does not conflict with any existing instructions. It shouldn't conflict with any existing instructions of the data. Thank you very much. And at the conclusion of my presentation, instruction formats play a vital role in determining how CPU processes and then execute instructions. And then a well-designed format can also optimize performances and then support a variety of operation efficiently. Thank you so much.
My name is Bright Rusa, and I'm here to present on the fetch, decode, execute cycle. I wonder you guys think about how computer processes instructions given to it. Every time we try to give commands and prompts, how it's able to process it. Well, it uses this cycle. That's the fetch, decode, execute cycle. So first, let's look at what it means. So the fetch, decode, execute cycle, also known as an instruction cycle, is a cycle that the central processing unit follows from boot up until the computer has shut down to process instructions. This is trying to say that as soon as you turn on a computer, it begins to the CPU begins to function. So any instruction that is given from that time, as soon as you try to boot the computer, it's also like an instruction given to it. So it turns off, powers everything, then it's ready to receive instructions and process it. So it is composed of 3 main stages: the fetch stage, the decode stage, and the execute stage. We'll be looking at these stages in the subsequent slides, but let's look at this little piece of information below. It says in simpler CPUs, every command is processed before the next one is initiated during the sequential execution of the instruction cycle. This is made possible by the cycle's division into independent phases, which enables the processing of the subsequent instruction to begin before the preceding instruction has ended. So they are like in simpler CPUs, like every command is processed before the next one is initiated. So it's trying to say instructions are processed once at a time. Like one has to be processed before the next one is initiated. But currently, in newer generation of machines, we have cores and CPUs, like cores. so it helps process information faster. So most times, like, you are able to process a lot of information in less time by using the old time, the simpler CPUs. Like, it takes a little bit of time, but in the new gen, with new generational computers, you're able to process info and instructions faster. So now let's look at some of the components in the CPU that are involved in the cycle. Number one, the program counter, the memory address register, the memory data register, the instruction register, the control unit, accumulator, and arithmetic logic unit, the ALU. Yeah. So now let's go to the stages in the fetch, decode, execution cycle. Number one, the fetch stage. Number two, the decode stage. Number three, the execute stage. Here is a diagram showing its order. So fetch to decode to execute and back to fetch again. And the funny thing about this fetch, decode, execute cycle is that it doesn't, when you reach when after an instruction is executed, it doesn't just end there. New ones come again. So it's like a repetition, a process. So it doesn't just stop then. It's done, because the computer is always going to be in use, and as far as you are going to be using the computer, instructions are going to be made. So this cycle has to repeat itself. So now the fetch stage. This is the first and the most important stage of the fetch, decode, execute cycle. During this stage, the CPU retrieves the next instruction from the memory address stored in the program counter and loads it into the instruction register. Following this operation, the program counter is updated to a point that the memory address of the subsequent instruction that will be fetched in the next cycle, ensuring the sequential execution of program instructions. So at this stage, this is where the CPU retrieve the next instruction from the memory address in the program counter. So the program counter points out the next instruction that's to be executed, but it's to pick this from the memory address, then copies it to the memory data register, which also all these are found inside the RAM. So the RAM is a random access memory. It means it can be accessed anytime you need to something from it, values from it, to like perform instructions and other things. So the memory address, then the memory data register are all found in the RAM. So the PC, the program counter, will copy this from the memory address and load it onto the instruction cycle. So, instruction register, sorry. So when it goes to the instruction register, this is where like we now reach the decode stage. So let's go to the decode stage of everything. It's like in the decode stage, the CPU analyzes the fetch instruction. It interprets the opcode to determine the operation type, extract operands or addresses, and identify the addressing mode for operand retrieval, such as direct or indirect memory addressing. The involved registers are also recognized. Source registers for data and destination registers for results. Control signals are generated to guide internal components, and the program counter is updated for the next instruction. This meticulous breakdown readies the CPU for the execute stage, ensuring accurate execution of the operation with the intended data and registers. So at this stage, the CU or the CPU uses this where like when it's copied, instructions are copied onto the instruction register, the IR. This is where the CPU decodes the instruction. So this is where the CPU will know which kind or how it's supposed to execute this. This is where it's to like know the operation type, the exact thing is to do. So it prepares everything for the CPU and breaks down every instruction very well for the CPU to execute it. So at this stage, after here, we move on to execute stage. The execute stage. The execute stage of the fetch, decode, execute cycle. The CPU performs the actual operation specified by the fetched and decoded instruction. This involves carrying out arithmetic, logic, memory, or controls operations depending on the instruction type. For arithmetic and logic operation, the arithmetic logic unit computes results using operands from the registers. Memory instructions involve interactions with memory to move data between registers and memory locations. Control instructions can change the program flow by modifying the program counter. The result of the operation is generated and stored. Condition flags might be updated, and the CPU prepares to proceed to the next instruction by updating the program counter. So from the decode stage, we come here. This is like the last stage of everything. So here, after the decode stage and then the fetch stage, where the instruction has passed through and has been decoded, and now the CPU knows the exact thing it's supposed to do. So now this way we need this place, the accumulator, then the arithmetic logic unit. The accumulator will hold the instruction that has been decoded. Then the ALU, the arithmetic logic unit. This one is for operating all arithmetic and logic operations. So anything from the accumulator will now be moved to a ALU, then it will be executed there. Every operation will be done there. Then from this stage, you move back again to the fetch stage again. That's where everything will begin again for new instructions. So after this, the program counter will be updated again and ready to receive new instructions again. So there's a diagram here that will show you everything, a summary of everything here. So here we have the start cycle. From the start of the cycle, the address in the PC is copied to the MAR, that is the memory address register. Yeah, so the PC copied address in PC is copied to MAR, the memory address register. Then it moves to the next stage. The PC incremented to points to the next instruction. So the PC will now point the next thing that is to happen with this instruction. The instruction found at the address described by the MAR, the memory address register, copied to the MDR, that is the memory data register, So the memory data register and then the memory address register, they are all found in the RAM, and that's where the PC or the program counter takes this instructions from. And then the instruction in the MDR is copied to the CIR. So instructions from the memory data register will be copied to the computer instruction register. So that's the end of the fetch stage. Then we'll now move on to the decode stage, which contains the place where the CU, the control unit, decodes the contents of the CIR. So this is where the control unit will decode the instructions, break down everything into like it will break down everything to the level that the machine would understand and know that this is what it's supposed to do. Then from there we now move to the execute stage. The control unit sends signals to relevant components, as I mentioned earlier, the arithmetic logic units, then the other the accumulator. Then that's where the instruction is executed. Then it ends here. It doesn't just end here, but it goes back to start again with new instructions again, and goes through the same stage, goes back again, continues with new instructions every time. So
Hello everyone, I'm Silat Sanjay. I represent Group 1 and I'm here to discuss about interrupts. In this presentation, we will uncover how interrupts shape the way our computers function. Let's begin this exploration into interrupts and discover how they contribute to the seamless operation of our computers. First of all, what's an interrupt? Interrupts are notifications of urgent events sent to the CPU by hardware or software. They only react when necessary, preventing the loss of CPU cycles. Inside a computer, each and every operation is guided by the interrupts. If you press any key on the keyboard, interrupt is generated. If you want to watch a movie or see something, the monitor interrupt is generated. To do printing or clicking on the mouse, interrupt is generated. Each and every operation is controlled by the interrupt. We have types of interrupts. There are two primary categories of interruptions. One, we have interrupts caused by external hardware, such as keyboard input, mouse clicks, or network connectivity, are known as hardware interrupts. They give peripherals a channel of communication with the CPU. So we have software breakdowns. These, which are also referred to as exceptions or traps, are brought on by particular program situations like division by zero or system calls. They aid the operating system in keeping a grip on program execution. What are the purpose of interrupts? Interrupts allow the CPU to switch between activities as needed. Interruptions make multitasking effective. We move on to interrupt handling process. Yeah. We have the IRQ, which is the interrupt request. A signal is sent to the CPU by an external hardware device to signal an occurrence. We have the ISR, that is the interrupt service routine. The ISR is a particular piece of code that the CPU performs after stopping the currently running task, saving its state, and handling the interrupts. We have the interrupt vector table. This table stores addresses of ISRs for various types of interrupts. The CPU uses the interrupt type to index the table and locate the appropriate ISR. We have the interrupt priority. Depending on their priority, some interrupts may be handled in a different sequence than others. This is the diagrammatic representation of the interrupt handling process that I was talking about right now. Then we move on to interrupt vector table. The interrupt vector table is a table of memory addresses of interrupt handler routines. The addresses of the ISRs corresponding to the various types of interrupts are kept in the interrupt vector table. A data structure. A distinct interrupt type is represented by each and every entry in the table. The CPU consults this table when an interrupt happens to determine which ISR to run. Here is the diagrammatic representation of the interrupt vector table. Then we move on to maskable and non-maskable interrupts. Interrupts can be categorized as either maskable or non-maskable. What do you mean by maskable interrupts? Maskable interrupt is a hardware interrupt that can be disabled or organized by the instruction of CPU. The CPU has the ability to mask or disable certain interrupts. They are often employed for less important events and free up the CPU to focus on tasks of higher performance. When maskable interrupt occurs, it can be handled after executing the current instruction. And we have the non-maskable interrupts. The non-maskable interrupt is a hardware interrupt that cannot be disabled or ignored by the instructions of CPU. These interruptions cannot be turned off. They are safe for urgently needed critical occurrences like hardware malfunction. This is telling us that some executions are more important than the other. So they fall under either maskable or non-maskable. Non-maskable interrupts are interrupts that are more important. So that kind of interrupt can never be disabled or ignored. But the maskable interrupts, they can be ignored or disabled to perform maskable interrupts before it can resume its execution or continue with its execution. Then we move on to the interrupt latency and priority. The duration between the moment an interrupt occurs and its related ISR starts running is referred to as interrupt latency. Many things, including as program effectiveness, interrupt priority, and hardware design, can affect latency. Low latency is typically experienced by high priority interrupts to guarantee prompt handling of important events. Then we can move on to importance in real-time systems. Interrupt management is essential in real-time systems. For these systems to keep functioning properly, external events must be responded to immediately. The method required to achieve rigorous timing specifications and guarantee that the system reacts immediately to time-sensitive events is provided by interrupts. It decreases the waiting time of the CPU and it stops wastage of instruction cycle. So the instruction cycle this is a diagrammatic representation of the instruction cycle that I just mentioned right now. It starts from the initiation, then it comes to the fetching stage, the decoding stage, the reading of address, then execution will take place. And as we all know, a cycle starts again from where it stops. So it runs in that order. Then in conclusion, modern computer architecture is built around interrupts. They make it easier to multitask effectively and manage events and respond quickly. Interrupts improve the overall effectiveness and functioning of computers by enabling the CPU to react to events as they happen. Thank you very much.
Hello and welcome once again. My name is Denchi Boateng Kwame. I'm in Group 1, and my job here today is to provide a summary on what my other members have already explained in the previous videos. So we are just going to move on to the instruction cycle. We are going to look through the instruction formats, and we are going to look through the fetch decode instruction cycle, and lastly interrupts. So without wasting much time, let's start with the instruction cycle. So in the instruction cycle, it is a process by which a computer executes instructions. It consists of stages such as the fetch, decode, execution, and read address from memory. So according to the slides I prepared, we are just going to move straight into that one because this is just a summary. Yeah. So when we talk about the instruction cycle, a program residing in the memory unit of the computer consists of a sequence of instructions. These instructions are executed by the processor by going through a cycle for each instruction. In a basic computer, each instruction cycle consists of 4 stages, which is the first instruction from memory, decode the instructions, read the effective address from memory, and lastly, execute the instruction. So there is a diagram for it which I'm about to show you. Yes, so this is a diagram which my fellow colleagues have already explained. So I'm just going to take you through one by one. So when we talk about the fetch instruction, the processor fetches the instructions from the memory. So that is basically it. Then we go to the decode instruction. Now with the decode instruction, it is a bit different. So the fetch instruction is decoded to determine multiple to determine the operation to be performed and the operands involved. So now with the decode instruction, it just uses the 3 by 8 decoder to decode the instruction. So we are going to go to the next one, which is the read address from memory. So now with the read address from memory, the computer just takes the decoded instructions, then it just read it to the memory. And lastly, then we go to the execute the instructions. On the execute instruction, the decoded instruction is executed by the processor, which performs specified operations using appropriate data and registers. Yes, so this is the summary on the instruction cycle. So our next topic we are going to look at is the instruction format. So in the instruction format, so the summary on instruction format is when we talk about instruction format in computer architecture, we are referring to the structure and organizations of instructions that a processor can understand and execute. So yes, that is the main idea about the instruction format. So what is an instruction format per my slide? An instruction format which specifies a computer instruction. The bits of instructions are divided into groups called fields. The most common fields are the operation code. When we say an operation code is a field which specifies operation to be performed, such as the addition, the subtraction, and the multiplication. So the next field is the address. When we talk about an address field specifies a memory address or processor register where operand is stored. And the last field is the mode. When we say a mode field is basically the field which specifies the way the operand or the effective address is determined or located. Yes. So there are types of instructions and types, or you can say types of address instruction. One, we have the general register organization, which the three address instruction format falls under it. Then we have the two address instruction format, which also fall under it. So the next type of instruction format is going to be this single accumulator organization, which under it the one address instruction format falls under it. And the third one is the stack organization. So under it, the zero address instruction format is also under it. Yes. So we are just going to go through the next topic, which is the interrupt. All right. So what happens when the microprocessor is interrupted? If there is any interrupt, if there is any interrupt that accepts and send the INTA into bracket low signal to the first graph. When the microprocessor receives an interrupt signal, it suspends currently executing the program and jumps into an interrupt server routine, which is known as the IRSR, to respond the incoming interrupt. The vectored address of particular interrupt is stored in the program counter. Each interrupt will mostly probably have its own ISR. Responding to interrupts. Responding to interrupts may be immediately or delayed depending on whatever the interrupt is maskable or non-maskable and whether the interrupts are being masked or not. So basically, there are two ways of redirecting the instruction to the ISR depending on whether the interrupt is vectored or non-vectored. Now, when we talk about vectored interrupts, a vectored interrupt is an interrupt which the subroutine is already known to the microprocessor, and the non-vectored interrupt is the one which the device will have to supply the address to the subroutine to the microprocessor. Okay. So there are types of interrupts. There are basically two types of interrupts, which is the hardware interrupts and the software interrupts. Okay. So this is the diagram of the interrupt cycle. It has the start, the fetch stage, the execute stage, the interrupt stage, and the interrupt disabled, and so on and so on. My other colleagues have already explained it, so this is just a summary. I'm going to move on. So now the next topic, we are going to go to the fetch, decode, execution cycle. Now the fetch, decode, execution cycle, it needs no further explanation. It is just like the instruction cycle. It moves and moves over and over again. Yeah, so the fetch execution cycle is the basic cycle of a computer. The cycle repeats over and over again from the moment a computer is turned on until it's turned off. Each time the cycle is irritated, a single machine code instruction is fetched from the main memory, decoded and executed. The results into bracket output of the instruction is usually stored into a general purpose register, but could also be written back to the main memory. So there you go. There's the diagram for the fetch, decode, execution cycle. And yes, that is also. Thank you for your audience. I appreciate it.